welcome to this webinar. As mentioned, I'm Dave Hughes, CEO of HCC Embedded. I'll give you a very brief background to HCC Embedded in context of what is relevant here. Well, we founded the company in 2002, specializing in embedded systems. Our very first products and the first things we started to work with was embedded flash, NOR flash, NAND flash, and trying to make file systems reliable. At the time, many embedded systems used a standard FAT file system, which is notoriously unreliable. And equally, NAND flash and NOR flash were being used with these unreliable file systems, and it is a real challenge to create systems that were reliable and you could depend on the data. And of course, in many embedded systems, the stability of the data is extremely important. As we grew as a company, we've branched out into networking, security, USB protocols, always deeply embedded components developed to higher and higher qualities for the embedded market. And more recently, I mean, we're now an ISO 9001 certified and audited company and ISO 27001 as well. And these are a continuing focus on quality, which is built out from our desire to make file systems on embedded systems fail-safe and reliable. We very much work with customer projects. We have over 2,000 customer projects in all industries, all over the world. We have file systems running on drill bits at the bottom of the North Sea. We have file systems that have been hung around bears' necks in Canada to track bears, where it was very important to get the data back. And we're currently working on file systems to go on the next space shuttle, the Dream Chaser, for launch next year. So we have a wide variety of experience of storing data to deeply embedded systems. And today I'd like to reflect quite a lot on how you make, the considerations you make when you want to make an embedded system, the data stored in an embedded system, reliable and fail-safe. So the first thing to look at is exactly what is a file system, what is its role? A file system is a method of hiding storage media from a user application. Like everything in computing, you want to make it modular and scalable. This is how we build desktop PCs. You get microcontrollers, you get components, you put them together, you build more and more complex systems. File systems is just another case of this. The file system is abstracting the media. So you can write a user application that doesn't know what it's storing its data to. All that's important to it is the data is stored reliably, and when it gets it back, it gets it reliably. What happens below that is not terribly relevant, except there are certain factors that do depend on the exact nature of the storage that can't be abstracted by the file system. And in particular, those are things like the performance, how fast you can write to it, how fast you can read from it, and how long the data will be safe on that system for. So there are parameters that are not abstractable by a file system, but by and large, the job of a file system is to create a user application interface, an API, where you can write your data and read that data back at some point in time and modify that data and not have to care what the storage media is. So at the high level, we have a user application. Its only concern is the file system API. Here I have a FAT file system. I can put any file system here as long as the API stays consistent. And then we have a media driver interface to that file system, whose job is, depending on what our storage media is, with NAND flash, SSD, eMMC, it doesn't matter. The file system API is abstracting everything so the user application can write open file, write to file, read from file, close file. And obviously there's much more sophisticated functions like volume management, directory management, etc. Pure core process here is we're going to try and hide as much as we can from the user. He just needs to care about his data. So then what do we mean by a fail-safe file system? Well, back in the days, a long time ago, most of the original file systems were not designed to be fail-safe. The FAT file system, which is notoriously unfail-safe, was specifically designed in the 70s with the idea that power would never fail. Now, of course, since the 70s, we've had a few power cuts and a lot more things that are unstable. We have battery-powered devices and things. I have no idea how they managed to keep their power so stable in the 70s, but FAT file systems were notoriously unstable. And one of the core problems was that you had an area where you stored the clusters, which are the units of data allocation, another where you stored the directory entries, and then you had the data itself. And it wasn't possible to atomically update any one of these. So if you changed one, you then had to make several other changes. So if you switched off power at the wrong moment, there would be an inconsistency, and then you had to run your checklist program and hope it could fix it. And in many cases, it required user intervention, or you could lose a whole disk. So the idea, what a fail-safe file system is to HCC is it's something that can provide a very specified level of functionality to the user. So a user application can trust in what they see from the file system. And it's crucial that at all points in time, we understand that it is a very clear definition. You can't just say a file system is fail-safe and then a user application can just use it. It's important for the user application to understand exactly what that fail-safety gives to the user. And then they can program, they can design their system in a reliable, predictable way. And so these definitions, these understanding the requirements, understanding the specification is extremely important. There are many file systems out there that make fail-safety claims. And indeed, they almost certainly are fail-safe in the right context. But the clue here is in the right context. Excuse me. For instance, on Linux systems, there are about at least four file systems that claim complete fail-safety. But many people test them and find they're not actually fail-safe in practice. I am almost certain this is not a failure in the file system itself. It's a failure of understanding how to integrate to the system and what that file system is actually providing to the user and what you have to support that with in terms of drivers. People writing board support packages for Linux devices don't have any idea what type of file system, what the requirements of the file system are when they write their NAND controller software. So there's a break in consistency here. So the important thing is that we have to specify exactly to the user what is required, what they're going to get from our file system. And so by fail-safety, it's a specified behavior that can ensure the data is always in understood and consistent state. This is what we're trying to achieve. So as I've already hinted, it's clear that you cannot take a file system in isolation and say it is fail-safe. It is completely dependent on what it's storing it to. If you imagine that you remove the disk completely, then the file system clearly cannot be fail-safe. So you have to guarantee a level of service from the storage media to the file system, and that's usually through a media driver to the file system. Equally, the user cannot assume that a file system is going to be fail-safe in the way it anticipates. So the file system has to be very clear in the service it operates to the user, so the user writes his application in a way that is consistent with the fail-safe claims of the file system. So these things have to all be taken into consideration. And of course, apart from the possibility of the media getting removed or corrupted, there's also the issue of power failures, system crashes, unexpected resets. And the only way to make a system fail-safe is to consider all of these aspects when trying to provide a level of service to the user. So you can write your user application knowing that when you write a piece of software, the data you read is correct and consistent. So following the system level approach and looking at the layers of our file system, what we need to do is define layers of quality of service that each layer provides to each layer above it. So the user application, when I write my user application, this is the one that's going to require the data to be stable. The one that's reading the data of where my bear went for 6 months in the forest and comes out when we pull a drill bit up from the bottom of the North Sea. and it's got data about what actually happened down there, the important thing is that what the user application gets back and what it sees when it reads that data back and how it wrote that data to it. And for us, the level of quality of service all our fail-safe file systems guarantee to a user application is that a file we will change a file atomically from one state to the next state, and that's done at the user application's command. And the files always have to be consistent. So these are the things that we will provide to a user application. So one of the problems with user applications is if you're writing a stream of data like to a database, you might be writing, you might seek into a file to one position, modify some data, seek somewhere else, modify some more data. The question is, at what point is this whole thing consistent from your point of view, from the application's point of view? Well, we say that at a certain point you call flush or you call close and open, and that syncs your data with the disk. But we do this on a file-by-file basis, so it's not the whole disk. And in that way, the user can decide at what point we will atomically change from one state to the next. And if the operation is complete, then obviously you will get the new state of the file with all the modifications that you made since you last synced the file. If the operation is not complete and say the power goes off, there's an accidental reset of the system or something and it comes back and the operation hasn't been complete, then we will restore the file to the state it was in before that set of operations was started. So we always have a state of before the last flush always stored. And this is what we mean by giving a quality of service from the file system to the user application. And the user application can rely on to trust his data, to trust the data and know exactly what they're going to get back. They don't have to do things like database rollback to hope that they get back to the clean state of the database. They can know they either got the database before it was updated or after it was updated and no intermediate point. But for the file system to be able to guarantee that layer of service, it needs to use something that guarantees a quality of service. So it needs a quality of service from its media driver. So here we specify what we require from the media driver for a file system. And so for most of our file systems, what we require of the media driver is that when we write data to it, it's written to the media in the sequence that we provided and that it's atomically updated. So in other words, when you write something, it either commits it or the previous state of that particular block that it was written to was still in place. We also insist that if an operation fails, it reports an error so that we know that we have to take action to repair things. That the data we thought was going to get written to the disk has not been written. We need to know that that operation failed. We allow it to be interrupted at any point in time and reset, but as long as if a write is complete, it must report an error. If you're doing a sequence of writes, they must be written in order. And one of the things is, I mean, in complex systems, lots of data gets written in parallel, particularly on things like SD cards where they're optimizing for performance. They remap data within the flash. And sometimes sectors get written in very different orders to which you commit them for this because they're optimized for performance and not for fail safety and reliability. But if we can't guarantee that data is written to the disk in a sequential way, so we update something and then something later gets updated, then we can't do the basics of ensuring that an operation is closed consistently. And without being able to do that, we can't guarantee fail safety. So what we require of the media driver is that we write sequentially and we atomically update and we report errors. And likewise, for the media driver to be able to provide this level of service, it needs the media to be able to provide the level of service. And it's roughly the same requirements of the media driver. It has to be updated atomically and it has to be committed in the sequence to which it's provided. Without that, it's very difficult on an embedded system to guarantee fail safety. Again, I can only re-emphasize the point that a file system cannot guarantee fail safety in isolation. You need to take a system view of it, Each layer must understand what it needs to provide to the layer above it and what it's getting from the layer below it. Without these conditions, no claim of fail safety has any real meaning. So just to summarize what we do, and particularly from a user point of view, if you write to a file, the file is in its pre-open state or its pre-flush state, or it is atomically swapped to the next state at the command of the user of that file. So the user has complete control over the state of the file. In this way, they can write an application without having to care about what's going on, the details of how you do flash management, what the media is, what the file system is. As long as we can guarantee these two things to the user application can be written without too much worry about consistency. It means things like database rollback is not necessary if you can guarantee this sort of completeness. And to summarize from the file system, from the media driver, what a fail-safe file system needs from a media driver, it needs to ensure that the sectors written to the media are done in the order that the media driver receives them, and it atomically updates the state of a sector. It can't leave a sector in a partially updated state. It either has to update it or it has to leave the sector in place. And it can survive one failed write, but that failed write must be reported to the file system so the file system can take appropriate action. So to get into more of the details and give you an idea of the problems with flash and media, I'd like to describe a little bit how flash translation layers work. Basically, all SSDs, SD cards, USB drives use a flash translation layer. They have blocks of NAND flash stored, and they have a controller which does a remapping. And so at the higher level, you have an application interface which writes from 1 to max sectors, or 0 to max sectors minus 1, however you want to look at it. And this is just a logical interface that the file system uses to write data. It is processed through a flash translation layer which remaps this to different areas of the flash. The reasons for doing this remapping are multiple, because the flash in these devices, SSDs, SD cards, has all sorts of complex error conditions. It is made with some bad blocks in the manufacturing process. So always there are some blocks that don't actually work and have to be mapped out of the system. There are issues with read and write disturb. When you write to one page, it may affect the stability of another page. If you write to one page, it may disturb another page. So you have to carefully manage how you write to the flash itself. So you can't just use this application interface to map directly onto here, because you don't know about the disturbances you're causing elsewhere. And it's the job of the flash translation layer to manage these things. And another very complex part of flash management is things like marginal programming. If you start programming to this device, this NAND flash, a page in here, for example, what could happen is that that program could be in progress and the power goes off. And when the power comes back, you read that page and it's actually correct. It actually looks as if it's correct. But because you haven't applied the power long enough, because the whole operation was not complete, you hadn't actually got to the point where the write was complete, that data may be long-term unstable. Because when you're programming a flash page, you have to apply the voltage and get all the voltage of the cells to a certain level before it can guarantee how long that data will survive for. So normally a flash device will say data retention of 5 years or 10 years, but that only applies if it's been programmed correctly. But if you power it off at the wrong point in time, you can end up with something that looks like it's programmed correctly, but its voltage is not at a high enough level to give its data retention, and so will weaken much faster over time. And that will make your file system inherently unreliable. If your data becomes unstable, if it's a core part of your fact table or something, or a directory entry, and you read that back later and it's no longer valid, then you've killed your file system. So the job of the flash translation layer is to hide all these complex details of flash management from the file system. And the complexity of the media driver is trying to use that translation layer to guarantee this level of service we specify, which is that writes are sequential and that any write errors are reported, and that you write atomically and there are atomic updates. Once we can guarantee all these things, then we can transfer that quality of service to the file system. The file system can do its job from a software point of view and guarantee the level of service to the user application, which is what we're trying to achieve. So obviously in embedded systems, if you're interested in having fail safety, if you're very concerned about the reliability of your data, one result of what we've just been talking about, or I've just been talking about, is that you have to be very careful about your choice of media. And so I have a table here that kind of summarizes media choices you might make in an embedded system and how it affects your fail safety in particular. So SD and eMMC cards, can they be fail safe? Well, this is difficult. I mean, most SD eMMC cards on the market are sold because of their speed. They sell speed and price are the two things. So you go down your local shop and they will sell you an SD card. They will boast about how cheap it is. They will boast about how fast it is. What they won't boast about is how reliable it is. They fail to write on these cards that they are, most of them are really fundamentally unstable. If you want to use an SD card that is reliable, that guarantees a level of service when it gets unexpectedly reset, then you need to pay a lot more for an SD eMMC card. And you need to verify that as well. So, I mean, HCC has test systems where we put cards into, and we batter the cards. We do resets on them, we program, and if the manufacturer states that this card is fail-safe, and we test it, then we'll accept that it can be used as a reliable storage of data. And you have to be very careful with the specifications. We've seen SD cards that say that they're fail-safe during read. Well, we don't really care about read because the contents of the cards are not changing. The time we need to be fail-safe is when you're writing to them. So if you're concerned about your data, you have to be extremely careful about which SD cards you use, and you're going to pay considerably more for an SD card that will give you a guarantee that the data will not be destroyed if there's an accidental reset or loss of power or a falling power voltage while you're programming. You have to be very careful. USB drives, the situation gets even more complex, and as far as we're aware, there's no USB jump drive that claims to be fail-safe because they have to go through USB host controllers and then into the manage the device itself. It's got the same flash translation layer that SD eMMC cards have, but it's got a more complex programming interface. And so when these are being programmed, I don't think any USB drives make the claim to be fail-safe because of the USB protocols in between the drive itself and the file system. So it's very difficult to make a USB drive fail-safe. Probably the only way to increase the likely reliability of these things is to make sure you've got some backup on the power so that you only have a controlled reset of the device. However, that always gives you a problem because if you have an accidental reset of your system, then of course, it doesn't matter how much power protection you've got. If it's in the middle of writing, the system resets, then you're in danger of corrupting your USB drive. eMMC is basically an SD eMMC card on a chip. And these were also designed, the specifications, the JDEC specification of eMMC have options for programming them in a way that they are reliable. Now, programming them so that they are reliable to their fail-safe takes more time and in some cases reduces the capacity of them. So eMMC can be managed to be fail-safe and then is a very reliable NAND flash storage media. But you have to make sure that your driver is written in a way to do that, to use the properties of that eMMC. And then two other methods of storing is to use raw NOR flash and raw NAND flash. Raw NOR flash could be the actual microcontroller's own NOR flash, which we sometimes do file systems for, but also it could be an external NOR flash, particularly serial NOR flashes. And of course, these can be managed because we can write media drivers that handle these directly. They're obviously complex and require a lot of management, but we can make them fail-safe, and as long as you build the right hardware around them. You have to have brownout detection. So if the voltage is falling while you're programming them, we need to get an alert so that we can fail a write that's coming in and tell the system, hey, this is not going to work for very long. You can't trust what you're writing to it. It's time to reset the system and try and bring the system back to a stable state before you carry on using the file system. And the same applies to NAND flash. NAND flash is obviously a lot bigger, can be a lot faster, particularly on writing. The erase speed of NAND flash is much higher than NOR flash. But if the trade-off is kind of with NOR flash, it tends to be more easily reliable. It requires less hardware support. NAND flash is cheaper per bit, but only if you need large numbers of bits. If you don't need large numbers of bits, then serial NOR flash is probably your optimal media. But with both of these, you need a flash translation layer in software and the right hardware support to manage the device, to ensure that you don't have accidental resets or drifting voltages on the devices that will cause unreliable data storage. So that's kind of a summary of the kind of embedded medias that you would have to consider and the issues you face when designing, when you want to have a reliable data on your embedded system, when you want fail safety. So as I mentioned, HCC have been developing file systems since the beginning of this millennium, really, and specialize very much in fail safety. Because embedded systems are so varied, some people say, oh, I've only got 32 megabytes of RAM. Some people say, oh, I've got loads of RAM, I've got 64K. The embedded world is very, very varied. And as a consequence, we've ended up developing about 8 different file systems for different purposes, for being FAT compatible, for managing flash directly, for working on a microcontroller with 1K of RAM and 10K of ROM, for working in a smart metering environment where you just want to do data logging. We've had to come up with different solutions, but one of the consistent themes for all our file system solutions has been that fail safety is the thing that we really focus on and is our main expertise. This diagram shows all the different file system options and how you interface to them. So we have a common file API, which you access most of our file systems, FAT, SaveFAT. So SaveFAT is a proprietary version of a FAT file system that allows us to make a FAT file system fail-safe. We've got an exFAT, same system, a SafeXFAT, which again allows an exFAT system to be fail-safe. And then we have file systems that map directly onto NAND flash and NOR flash, including a tiny version specifically for very small microcontrollers. And some of these file systems use standard media driver interfaces so that we can use things like a USB host controller and a pen drive or an SD card, an eMMC, or talk through our flash translation layer to NOR and NAND flash. And so all these different configurations allow you to optimize the fail-safe file system solution for your embedded application, depending on what your requirements are. Are my requirements speed, size of disk, RAM usage? We have all different options to try and cover the different possibilities here and guarantee fail safety. So I'm not going to go into the details of this table, but this table summarizes our different file systems and whether they're fail-safe and the types of media you can use with them. And the aim here is that regardless of your embedded application, by doing analysis and taking a system-level view of what you're trying to achieve, what your user application needs, you can select the right component, the right mix of components to be able to store your data in a fail-safe way to your embedded system. But coming back to this original diagram, I'd like to explain some of the complexity of file systems and file system storage, and why we have one alternative solution, which is our smart metering file system. If you look at this diagram, if you've got a user application, if I'm trying to do something like store a meter reading every second to a log, or maybe it's the position of a bear in Canada moving around every every hour or every day or something, or it's a wave moving up and down in the middle of the Atlantic Ocean. I'm trying to store this over and over again. When you want to store this through a standard file system API, the user application has to open a file, it has to seek into the position of the file, add the data, and then close the file to make that fail safe. That gets done in the file system, but when that gets translated to the media drivers, then if you remember the flash translation layer and the remapping, all those operations have to be remapped through a flash translation layer onto a NAND flash or a NOR flash. That might happen directly by something on your embedded software if you're directly addressing these flash devices, or it might happen through a controller in the case of an SD card or an SSD. And the thing here is that, so to write a simple piece of like 10-byte record of the position of my bear, it's going through a lot of operations and translations in the file system, move to position the file, close the file, which gets translated into a lot of operations to make that fail-safe on a NAND and NOR flash. And that's why we developed our smart metering file system, which is more a data logging type file system, which allows you to map your user application directly onto the flash, or map your embedded database directly onto the flash. So this file system here, the smart metering file system, is designed for use on serial NOR flash, where we can reduce the number of operations to store a data logging record onto a flash. We can reduce that by maybe an order of magnitude, which creates a better fail-safety. And by better fail-safety, what I mean is that it is fail-safe, but it's fail-safe with a lot fewer operations, which means that we have less disturbance on the device, and a physical flash device will last a lot longer. If you reduce the number of operations on a NOR flash, then you can either use a smaller NOR flash, which can save you money, or you can you get a longer data retention. It'll last 10 times as long if you reduce the number of operations on the flash by a factor of 10. So the point of this is that by analyzing the system and deciding what you're really doing with your data, taking a system-wide approach to how we look at the file system, we can find very highly optimized solutions for fail-safe storage of your data to an embedded system. So that kind of brings me to the end. I would like to make the key takeaways from what we're trying to get over here, what I'm trying to explain about designing reliable storage for embedded systems. The most important things is, firstly, you have to take a system-level approach. No file system is fail-safe in isolation. It has to be done in the context of the power supply, in terms of the storage media used, in terms of what your application needs to achieve. All these things have to be understood. And without understanding these things and without taking this system-level view of your storage, you can never claim fail-safety. You can never claim it's going to be reliable. Once you have a system-level approach and you've decided what's needed, one of the things you will have to do is define the quality of service that needs to be designed between each layer in the system, between that user application and that file system, between that file system and the media driver, between the media driver and the media itself. At each stage, the quality of service that's going to be provided by a layer has to be understood and acknowledged by the layer above to make sure that's enough to be able to guarantee the fail safety. And in each case, not only do you have to specify it, you also have to test it and verify it. So we build large test systems, and we insert errors in low-level drivers to make sure that where things do go wrong, the layer above can handle that situation and properly process it. So the quality of service needs to be designed, understood, and proven between each layer if you're going to guarantee fail safety in a system. And the third big takeaway is the media, and in particular flash media, needs particular expertise. Flash media is complicated. Things like read disturb, write disturb, the data retention, and marginal programming are all things that really require very specific understanding, and you really need to think very carefully when you're designing your system that if you're trying to provide that quality of service from flash to the media driver and hence to the file system, you do need very specialist expertise in trying to understand how that is achieved. So that brings me to the end of today's webinar. I hope it's been interesting and given you some ideas about the complexity and the challenges facing reliable storage to embedded systems and how to create a fail-safe file system. If you would like further information about our products or about our expertise, please contact Mike Muslik at Hitex or directly contact HCC Embedded, where we've got on our website, we've got lots of collateral about file systems, comparison tables, and user manuals explaining fail safety and all the issues regarding building an embedded system with fail-safe data storage. Thank you for listening. Goodbye.